Probably my #1 favorite assumption to make in engineering problems is steady state. This means that the system is not changing in time, and it lets you ignore basically everything that's complicated that's happening and treat it in the easiest way possible. But sometimes that's not possible. So if you take a cold metal plate and put it in a 700-degree oven and you want to track the change in temperature over time, then this is unsteady conduction or unsteady state, usually called one-dimensional transient conduction. And in your heat transfer course, you're going to learn 2 different methods to solve one-dimensional transient conduction problems. The easier one is the lumped capacitance, lumped heat capacity. And the more complicated version is going to be the one term approximation, which you'll probably see in a section called Sudden Convection. Now, each of these 2 methods don't work all the time. So before you use either of them, you need to actually check the Biot number and the Fourier number to verify that they're actually applicable to the situation. But for this problem, I'm going to solve this using both methods so that you can see how they both work, and then in your problem, you just choose whichever one you want. You don't need to use them both. So lumped heat capacity first. In order to verify that the lumped heat capacity assumption is valid, you need to check the Biot number, and you're hoping for a very small Biot number. The lumped heat capacity approximation essentially says that the entire object is going to be the same temperature. It's all lumped together as one temperature. You don't have a separate surface and centerline temperature, they're both the same. Now that only works if you have really good conduction in your material, so that if the surface temperature changes, that conduction happens like instantly and the center temperature changes right along with it. So you want really high value for K and a really then small value for H so that the surface temperature does not change very quickly. All right, your TA Serenity already took the napping spot here in the studio, so your TA Indiana went to go find a napping spot in the other room. Hopefully you'll come back and rejoin us later. Now normally when evaluating the lumped capacitance method, you're going to calculate the Biot number using HV over KA. But this term V over A is kind of problematic for us because we don't actually have the dimensions of the plate in this problem. If I were to call this a 1 meter by 1 meter plate, then I could calculate the volume as 0.03 meters cubed, and I can calculate the surface area as just add up the surface area of all 6 sides. I get 2.12 meters squared. And that gives me a Biot number about 0.01, which is a really good sign. You want to be less than 0.1. If you're less than 0.1, then you are good to go for lumped heat capacity method. But keep in mind, I just made up some completely fake dimensions here as I calculated this volume and surface area. So probably a better option for me, rather than just making up numbers, would be to assume that the thickness is negligible. That is, we're assuming that this plane wall is large enough that the surface area of like the front and back of the wall are much larger than the thickness of the wall, like the surface area of the sides. And in that situation, volume over surface area reduces to thickness divided by 2. And this value, thickness divided by 2, is going to be referred to as the characteristic length for a plane wall. Half of the thickness, right, is the characteristic length. And so I'm going to recalculate my Biot number using this assumption and using the characteristic length, and I get a value of 0.0109, which is very close to the number that I had before, and is essentially the number I would get if instead of choosing 1 meter by 1 meter, I had choose like 1,000,000 meters by 1,000,000 meters, right? When the surface area goes to infinity or when the thickness goes to 0, this is the Biot number, this is the characteristic length. But in the end, yes, less than 0.1, so the lumped capacitance method is valid. For every one-dimensional transient conduction example problem you work, this should be always the first thing you check. Check the Biot number and verify if you can use lumped heat capacity because this is the easiest method, so this is the one you want to use if you can. But since I'm doing both methods, I need to also check whether the one-term approximation method is valid. So the one-term approximation heat transfer method is going to account for the difference between the surface temperature and the centerline temperature. So you can get 2 different answers at the end, but the assumption that we're making is that time is sufficiently long. The one-term approximation does not account for the very first instant of convection after temperature changes. So the sudden convection, right when temperature changes, like the shock to the system, this one-term approximation does not account for that suddenness. But as long as you go a little bit further in time and you avoid that first sudden shock, then this one-term approximation is going to give you a good valid estimate. And so the Fourier number is what you need to calculate, and you want a Fourier number greater than 0.2. And so since time is in the numerator, the further in time that you go, the larger your Fourier number would be, and the more likely you are to satisfy this criteria. So we're given our value of alpha, the thermal diffusivity, which is 33 times 10 to the minus 6. We're trying to find temperatures after 10 minutes, which is also probably a good sign. That's a pretty long period of time, but remember to write in 600 seconds so the units will cancel out. And then the value of L, this is that same characteristic length. It's the thickness of your plate divided by 2. Because heat doesn't have to go from one side of the wall to the other side of the wall. The heat's only going from the outer surface of the wall to the center. And it's separately going from the other surface to the center. So the heat only is actually traveling like half of the distance to get to the center line. So some calculator work, Fourier number 90.4. So definitely larger than 0.2. So the one-term approximation method is valid. You can use, for this problem, either lumped capacitance or the one-term approximation. So if you see your TA Serenity's paws wiggling like this, she's clearly dreaming about transient conduction, trying to mentally help you out with this problem. So hit the thumbs up if you think she's helping you out at least a little bit. All right, so let's jump back to lumped heat capacity. That's the easier equation to use. You've probably got it in your textbook. I'll grab it from the FE reference manual. So the temperature on the far left here, that's the actual temperature we're trying to find. That's the unknown temperature of our plate after 10 minutes. So T infinity is the ambient air temperature. That's in like the oven here, 700 degrees. And Ti, that was the initial temperature that the surface started at, 25 degrees. We're given time, 600 seconds. So for this equation, that just leaves us with beta, which is the time constant, right? It's like the rate of change of the temperature of our object. And this time constant is HA over rho V Cp. We're given most of these values. Our H value was given as 80 watts per meter squared Kelvin. Density for a metal, 8530 kilograms per meters cubed. Cp, 380 joules per kilogram Kelvin. And then these same terms keep showing up, volume and surface area. So again, because we don't actually have the exact dimensions of this plate, we're sticking with our assumption that the thickness is essentially negligible, or that the surface area of the big rectangular is much larger than the side. So our V over A is just thickness divided by 2, which is the characteristic length, the 0.015 meters, which goes in the denominator because we're A over V, and the 0.015 is V over A. And another way to phrase this assumption is to assume that heat transfer is one-dimensional only through the big rectangular surfaces. We're not accounting for heat transfer through the little sliver surfaces out through the sides. Some calculator work, 0.001645 as our time constant, units are 1 over seconds. And some more calculator work with the e to the negative 0.9, whatever, 448 degrees. So this big metal plate started at 25 degrees. We put it in a 700 degree oven. After 10 minutes, it will be 448 degrees. And that's pretty hot, although still not even very close to the 700 degrees that it's in, so it actually still has room to go. If we leave it in there longer, it'll keep heating up. And for this problem, we were asked to find the surface temperature and the centerline temperature. Lumped heat capacity method says that those two temperatures are the same, so this 448 degrees is both surface temperature and centerline temperature. So the other method to solve heat transfer transient conduction problems is the one-term approximation. I'm grabbing the version of the equation from the FE reference manual. If you check in your textbook, you may have some of these terms like this C and this Greek zeta. They may be different variables in your textbook, but they still represent the same thing, and you're essentially just going to look them up in a table based on the Biot number. So using my Biot number of 0.0109, I'm almost right at the very top of the table. So normally with really low Biot numbers, you don't use one-term approximation, you just use lumped capacitance. So that's why most of this table is for larger Biot numbers, because you would mainly only use this method when you can't use lumped heat capacity, so when you do have a larger Biot number. But I can still flex my interpolation skills here a little bit and grab a C value and a zeta value in between these top two columns of the table. So I get 0.1035 for zeta and 1.0018 for C. So I plug these values into my one-term approximation equation. Also have to grab my Fourier number, the 90.4. I need that one also. Get a temperature, 443.2. And that is a centerline temperature. This equation here is for the centerline temperature, not the surface temperature, right? Using this method, the temperatures are different. We're actually accounting for the difference between the two. So now that I put the equation on the screen to find the surface temperature for the one-term approximation method, you'll see that it's almost exactly the same as the centerline. There's just an extra cosine term at the end. And now this may help you understand what this value zeta actually represents. Right, this value zeta that we looked up in a table, it's part of the ratio that affects the difference between the centerline and the surface temperature. This x over L is a ratio, with L being the total distance from the centerline to the surface. And then x is that distance. How far from the centerline to the surface are we interested in? So if we're interested in temperature at the surface, we use x equals L. So just L over L, and that cancels out. So just cosine of zeta will give us the surface temperature. So every other number in this equation is the same. The 700 degrees, 25 degrees, the 1.0018, the 0.1035, everything's the same. We just have this extra cosine term at the end. Oh, and before I type in the numbers, this equation for one-term approximation is only valid for a plane wall. If you have a cylinder or a sphere, there's going to be a slightly different version of the equation. So make sure you're actually mindful of the shape. This doesn't work all the time, only for a plane wall. And before you type numbers into your calculator, make sure your calculator is in radians. My calculator was in degrees and I got like a 0.9999 because 0.1 degrees is a super tiny number, so cosine was almost exactly 1. Now once I change it to radians, it's still 0.9946, but if you're like me and your calculator is normally set to degrees, make sure to really be mindful. This value zeta is a measurement in radians, not degrees. So now plug that number in, do some more calculator work. 444.6 degrees, that is my surface temperature for the surface of the wall using the one-term approximation transient conduction method. So to check our answer at the end, this unsteady state conduction one-term approximation method, we got a surface and a centerline temperatures, 444.6, 443.2. Only about a 1 degree difference from surface to centerline. And that makes sense because the lumped heat capacity method was valid. So if the surface and the center are only 1 degree apart, then yes, it's perfectly justified to just assume that they're the same. Now, it may seem kind of weird though that the lumped heat capacity number was 448. You and I probably would have thought that the lumped heat capacity number would be in between our two one-term approximation numbers. But that doesn't have to be the case. These two methods are actually like two different methods. Lumped heat capacity is not just an average of the centerline and surface temperature. Lumped heat capacity is just a separate technique. But even though this 4 degree difference looks like that's kind of big, like 4 degrees, remember that this is out of 440 degrees. A 4 degree difference is still less than 1% error, which is pretty good for engineering purposes. A lot of times a 1% difference is not that big of a deal. So next video is going to be more one-term approximation example problems, but instead of only doing a flat plate, we'll look at a flat plate and a cylinder and a sphere so you can see the different ways to calculate surface temperatures based on the different shapes of your objects.